Quantum physics, often referred to as quantum mechanics, is the fundamental framework that describes the behavior of matter and energy at the smallest scales of nature, governing the atomic and subatomic world in ways that challenge our classical intuition and reshape our understanding of reality itself. It emerged in the early 20th century when pioneers such as Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger confronted anomalies that classical physics could not explain, such as the ultraviolet catastrophe, the photoelectric effect, and the stability of atoms, leading to revolutionary concepts like wave-particle duality, quantization of energy, and uncertainty, all of which forced humanity to rethink the very notions of determinism and causality that had dominated since Newtonian mechanics. In essence, quantum physics tells us that particles such as electrons, photons, and quarks are not just point-like objects but also exhibit wave-like behavior, capable of existing in superpositions of states until a measurement collapses them into a definite outcome, a phenomenon dramatically illustrated by the famous double-slit experiment where individual particles fired through slits create an interference pattern as if they are waves exploring multiple possibilities simultaneously, only to behave like localized particles once observed, highlighting the deep mystery of measurement and observation. Quantum mechanics also introduces the principle of uncertainty, formulated by Heisenberg, which asserts that one cannot simultaneously know with arbitrary precision both the position and momentum of a particle, not because of technological limitations, but because nature itself is probabilistic at its core, governed by wave functions and probability amplitudes described by Schrödinger's equation, meaning that outcomes can only be predicted in terms of likelihood rather than certainty. This probabilistic nature challenges classical determinism and invites profound philosophical debates about free will, reality, and the role of consciousness, as some interpretations, like the Copenhagen interpretation, argue that measurement collapses the wave function, while others, like the many worlds interpretation, suggest that all possible outcomes occur in branching universes, making our observed reality just one among countless parallel possibilities. Beyond its philosophical intrigue, quantum physics has profound practical applications, giving rise to technologies that have reshaped modern civilization, such as semiconductors, transistors, lasers, MRI machines, atomic clocks, and the foundations of modern computing, while in recent decades the frontier has expanded to quantum information science, where principles of superposition and entanglement are harnessed to develop quantum computers capable of solving certain problems exponentially faster than classical computers, quantum cryptography that ensures unbreakable communication security, and quantum teleportation that transfers quantum states across distances without moving physical particles. Entanglement itself, famously dubbed spooky action at a distance by Einstein, describes the counterintuitive correlation between particles that remain linked even when separated by vast distances, such that measuring one instantly influences the state of the other, defying classical notions of locality yet confirmed repeatedly in experiments and enshrined in Bell's theorem, which shows that no local hidden variable theory can fully account for quantum correlations, meaning that reality is fundamentally non-local, or that information is woven into the fabric of the universe in ways still not fully understood. Another cornerstone is the idea of quantization, that energy comes in discrete packets called quanta, rather than continuous amounts, which Planck first introduced to explain blackbody radiation, laying the groundwork for the quantum revolution, and which underpins phenomena like electron orbitals in atoms, where electrons can only occupy certain discrete energy levels, leading to the characteristic spectral lines of elements and the very chemistry that makes life possible. The mathematics of quantum theory is expressed through linear algebra and Hilbert spaces with operators corresponding to physical observables, and though abstract, this formalism yields predictions tested to extraordinary precision, such as the magnetic moment of the electron or the behavior of quantum electrodynamics, which is one of the most accurate theories in science. Still, despite its success, quantum mechanics resists intuitive understanding, as thought experiments like Schrödinger's cat, a paradox where a cat is simultaneously alive and dead until observed, illustrate the strangeness of applying quantum superposition to macroscopic objects, raising questions about the boundary between the quantum and the classical worlds. Quantum field theory, an extension that merges quantum mechanics with special relativity, portrays particles not as fundamental objects but as excitations of underlying fields, and within this framework, Forces are mediated by exchange particles like photons for electromagnetism or gluons for the strong force, forming the standard model of particle physics, which unifies electromagnetic, weak, and strong interactions, and has been confirmed by discoveries such as the Higgs boson, while still leaving gravity outside its scope, pointing to the need for a quantum theory of gravity that might come from string theory or loop quantum gravity, though both remain under development. Experiments at colliders like CERN's Large Hadron Collider probe the high-energy frontier to explore phenomena predicted by quantum theories, and to seek answers about dark matter, dark energy, and the early universe, for quantum physics also plays a vital role in cosmology, where quantum fluctuations during inflation are thought to have seeded the large-scale structure of galaxies we observe today, while Hawking's application of quantum principles to black holes revealed that they emit radiation, suggesting deep connections between quantum theory, information, and space-time geometry. In laboratories, advances in controlling quantum systems, such as ultra-cold atoms, superconducting qubits, and trapped ions, are pushing the boundaries of precision measurement, leading to quantum simulators that can model complex materials, quantum sensors that measure time, gravity, and magnetic fields with unprecedented accuracy, and experiments that probe the limits of entanglement and coherence, offering not just technological advances, but also deeper insights into the foundations of reality. Quantum biology even explores whether phenomena like photosynthesis, bird navigation, and even consciousness itself may rely on quantum effects, though the field is still in its infancy. As we push forward, the quest to reconcile quantum mechanics with general relativity remains one of the greatest challenges. For while quantum mechanics governs the microscopic world, and general relativity governs the cosmic, their mathematical formalisms clash at singularities like the Big Bang and inside black holes, hinting at a deeper theory yet to be uncovered, one that could unify all forces of nature. Whether such a theory will emerge from string theory's vibrating extra-dimensional strings, from loop quantum gravity's spin networks, or from an entirely new paradigm remains unknown, but what is certain is that quantum physics has already reshaped not only our scientific worldview, but also our philosophical and technological landscape, showing us that the universe is far stranger, subtler, and more interconnected than classical thinking ever allowed, and as research continues, quantum mechanics will remain both a practical engine of innovation and a profound reminder of the mystery at the heart of existence, where particles and waves, chance and necessity, the known and the unknowable, dance together in the invisible fabric of reality that defines everything from the tiniest atom to